Welcome back everyone. In this lesson we are going to learn about spline interpolation. It's a special type of interpolation that is different from the other interpolation techniques that we have learned before, such as the Newton's interpolation formula or the Lagrange interpolation formula. So this technique is a slight different from the previous two ones. So let's go through the details of this spline interpolation. First of all, in the last few lessons, we have learned about Newton's polynomial and Lagrange interpolating polynomial. So say if we are given n data points, so we n plus 1 data points, so we can at most derive an nth order interpolating polynomial. So if you the order of the interpolating polynomial should be at most less than 1 than the data points. But there is a problem in these higher order interpolating polynomials, because let's say you have 8 data points, so you can actually derive at most 7th order polynomial. It could be either Newton's polynomial or Lagrange polynomial, whatever it is. But such kind of higher order polynomials sometimes do not give you the proper result. That means that it doesn't mean that always you will get better result with higher order polynomials. It is not always true, and that's why this is very these interpolation polynomials like Newton's or Lagrange interpolating polynomial, these are very much erroneous. So whenever you use a higher order version of these interpolations, so that's why we sometimes we prefer to stay in the lower order cases. So for those purposes, this spline interpolation has emerged. In this spline interpolation, we actually fit a specific type of polynomial within each interval of the data points. So that's what we are going to do in the spline interpolation. Let's look at this figure. In figure 1, we have a step function. You know what is a step function? The value of the function is 1 whenever the value of x is greater than 0, and at x less than 0, the value of the function is 0. So if you want to fit a polynomial, let's say you want to fit a Newton's polynomial here. So this is the Newton's polynomial. Let's say it's a second order polynomial. So look at this. The polynomial actually captures the main function very all I can say it is almost accurate but not so proper. So if I want to go for higher order interpolation polynomial, let's say third order Newton's polynomial, it would look something like this. Look at this. There are some oscillations here at these locations and at these locations. As a result, the function of the interpolating polynomial actually providing erroneous results here. Similarly, if you go for higher order interpolation polynomials, the oscillations becomes larger. So as a result of these interpolation polynomials do not provide you the proper results whenever the order of the polynomial is very high. On the other hand, if you had just used a linear interpolation at each of the intervals, that means let's say for these two data points you use a straight line. Similarly, at these two data points you use a straight line. Similarly, at each of the data points, between each of the data points, you use a straight line for interpolation purpose, then you will get a figure something like this. So look at this, the fourth one. This figure actually captures the feature of the data points very much accurately than these higher order interpolating polynomials. So you have to remember that the increasing the order of the polynomial does not mean that you will get a better polynomial curve. So sometimes the simpler lower order polynomials give you proper and better results. So that's why we are going to use the spline interpolation. Okay, what is a spline interpolation actually? Let's say we have some of the data points here. These data point, this is data point 1, 2, data point 3, data point 4, 5, 6, 7. So there are 7 data points here. So we want to fit a straight line between each of the data points. Let's say for the first 2 data points we fit a straight line. Similarly, for the second and third data points we fit a straight line. Similarly, between the third and the fourth data point we fit a straight line, and then similar for the other data points we fit a straight line. So this is the spline interpolation for the straight line purpose. Similarly, if we want to fit a higher order interpolating polynomial between each of the intervals, we can do that. For example, let's say I want to fit second order interpolating polynomials between each of the data points, and it would look something like this on the figure and on the second figure. So we are given some data points 1 2 3 4 5 6. So there are 6 data points. So in the first case, between the first 2 data points, we are fitting a second order polynomial here. Similarly, in this interval between the second and the third data point, we are fitting a second order polynomial again. Similarly, for the other intervals, we are again fitting a second order polynomial. So that's the spline interpolation. We are just fitting a specific kind of curve between each interval. In the Newton's and Lagrange interpolating polynomial, we did not fit separate interpolating polynomials between each curve. Rather, we had fit an overall curve which is much of higher order whenever we are given a large number of data points. But in spline interpolation, we can just fit a lower order interpolating polynomials between data points. Okay, so that's the main purpose here, that a lower order polynomial sometimes actually captures the best feature of the data between two intervals. Okay, so that's the spline interpolation. So first to the spline, I have already seen, I have already shown you how to fit a first order interpolating spline. You just fit a straight line between each interval. So each of the straight line is actually contain an equation something like this. For example, the first 2 data points, between the first 2 data points x0 and x1, we fit a straight line which looks something like this. F of x equal to f of x0 plus m0 into x minus x0. Here m0 is the slope of that straight line which is situated between these 2 data points x0 and x1. Similarly, next 2 data points, that means x1 and x2, we can fit another straight line, and in this way we can actually fit several straight lines or linear interpolating curves between each interval. So at each of these function, this function, this function, or this function, each of these function actually provide you the function within that interval actually. So each of them are different, okay, but each of them are of first order. That's why it is called the first order spline interpolation. These mi terms, m terms, that means m0, m1, m2, these are the slope of each of the straight lines. So these slopes can be easily determined by using this formula. This is the general slope formulation, the height divided by the base. The height is f of xi1, I plus 1 minus f of xi, that means the difference between the function values in that interval, and divided by the difference between the x data points. So this is very straightforward. M terms can be easily determined using this formula. So once we determine the m, that means the slopes, we can easily substitute that slopes into these equations, each of these equations, and we can easily determine a first order spline curve between each interval. So that is very straightforward for linear interpolation. But what about the other interpolations? If we want to determine, say, quadratic interpolation or cubic interpolation, that means if I want to increase the order of the fitted curve between each interval, what would look like those cases? For example, let's say I want to fit a quadratic interpolation between each interval. Okay, that means the quadratic interpolation, the curve would look something like this: f of x equal to a x square plus bx plus c. So each of these terms, ai, bi, and ci, these are the coefficient terms, and that should be determined. And f is the function value. This is the second order polynomial at each interval. So in the first interval, I use f1 of x equal to a1 x square plus b1 x plus c1. Similarly, in the second interval, I use f2 of x equal to a2 x square b2x plus c2. So the figure looks something like this. This is the function f of x, and we are given 4 data points: x0, x1, x2, and x3. Okay, so within each interval, there are 3 intervals. Since we have 4 data points, there will be 3 intervals. So within each interval, I actually fit a curve that is of second order. So within the first interval, I fit a second order curve which looks something like this: a1 x square plus b1 x plus c1. In the second interval, I again fit a second order polynomial, which is a2x square plus b2x plus c2. Similarly, in the third interval, I use again fit a second order in the interpolating polynomial, which is a3x square plus b3x plus 3. So in the each of the three intervals, I have fitted separate second order polynomials or quadratic polynomials, and that's why it is called a second order spline interpolation or quadratic spline interpolation. So we need to determine these coefficients a1, b1, c1, a2, b2, c2, a3, b3, c3. So all of these coefficients need to be determined to find out the function at each intervals. So our next purpose is to determine these coefficients. Okay. So there are n plus 1 data points, so which range from I equal to 0 to n. So at each interval, I have three unknowns. For interval 1, I have a1, b1, c1 unknowns. For interval 2, I have a2, b2, c2 unknowns. So for each interval, I have three unknowns. Since there are n plus 1 data points, so there should be n intervals. Since each interval contains three unknown coefficients, there will be in total 3n unknown constants. Okay, so that's the calculation here. We have to determine the 3n unknown constants. So for example, I have three intervals, then I would have to determine 9 unknown constants. If I have 4 intervals, I would have to determine 12 unknown constants. So these constants are actually the a, b and c constants. So we need to determine those constants. So I want to show you how we can actually determine these 3n constants. So if as there are 3n unknowns, so we need to have 3n number of equations. Okay, so by solving those 3n equations, we can easily determine the unknowns. So that's why I need to find out those equations, those 3n equations that are going to be used to find out these constants. Okay, so there are several types of these 3n equations. We can easily determine these 3n number of equations, and I am going to show you how these separate types of equations actually sum up to give you the whole picture. First of all, since each of the interval contains separate interpolating polynomial, that means at each of the junction, the function would have to be equal. That means in this curve, there are two internal knots. That means let's say we have an internal knot at x equal to x1. This x1, at this x1 we have an internal point. The boundary points are x0 and x3, and the internal points are x1 and x2. So according to the equation type 1, at this point x1 comma f of x1, these two curves, that means a1x square plus b1x plus c and a2x square plus b2x plus c2, these two curves are going to be equal. Okay. Similarly, the second interval point, at this point x2, these two curves a2x square plus b2x plus c2 and a3x square plus b3x plus c3, these two curves are going to be equal. So at each of the internal knots, we are going to have two functions here. Okay, two equations here actually. So at each of the internal knot, we are going to have two equations. So at x1 equal to 1, we are going to have two equations. Similarly, x2 at x equal to x2, we are going to have two equations. Okay, so look at this. With the first equation at this point, that means we are going to have ai xi minus 1 square plus bi xi minus 1 plus ci xi minus 1. That means the second equation. Similarly, this equation can be easily approximated as ai minus 1 x square by bi minus 1 xi minus 1. Similarly, so all of these two equations from at each of the interval points can be easily determined. So I have 4 data points here. So therefore I would have 2 internal data points. Okay, that means number of internal data points is less than 2 from the total number of data points. So if I have n plus 1 data points, I would have n minus 1 internal data points. At each of the internal data point, I would have two equations. So at n minus 1 internal points, I would have 2n minus 2 equations. So in our database, if there are n plus 1 data points, I would have n minus 1 conditions, and at each of the conditions I would have 2 equations. So therefore I would have 2n minus 2 conditions. That means under this category of equations, I would have 2n minus 2 conditions or equations. Okay, so this is the first type of equations that I am going to encounter in the quadratic interpolation. There are, but I have to determine 3n equations, but I have just found 2n minus 2 number of equations. I have to find other equations as well, and that's why we are going to move on to the next category of equations. At this equation type, if we see at the curve here, we see that at the boundary points the function values are equal to the endpoints. That means the first function at the first function at the first interval should go through the first point here. Similarly, the last function, that means a3x square plus b3x plus ct, have to go through the last data point, that means this one. So as a result, at these two boundary points we are going to find out another two equations. Okay, so under these category of equations we have just two equations. Okay, so till now I have found 2n minus 2 equations under category 1 and 2 equations under category 2. So in total till now I have found 2n equations. I have to find out other n equations as well. So that's why I am going to go for the third category. Under this category, the derivative of the interior nodes must be equal. So if you look at the picture again, at these data point x equal to x1, at all of the internal data points the functional derivatives should be equal. So at these x equal to x1 internal data point, the derivative of this function and this function should be equal. So the derivative of the first function is 2a1 x plus b1, and the derivative of the second function is 2a2 x plus b2. So these two terms are going to be equal. Similarly, in the next internal data points, the derivative of these two functions should be equal. Okay, so at each internal data point we are going to find out one equation that actually denotes the equalness of the two derivatives at the two intervals. So at each internal data point, since I have n plus 1 data points, so that means I would have n minus 1 internal data points, and that means I would get n minus 1 conditions or equations. Okay, so up until now what I have got under the type 1 category, I have found 2n minus 2 equations. Under the second category I have found two equations, and under the third category I have found n minus 1 equations. So in total I have just found 3n minus 1 equations. But if you remember, at each interval we have 3 unknowns, so that means I would have 3n equations, but I have just found 3n minus 1 equation. That means there is one less equation that I have to find again. So what is that equation actually? Since there are no conditions to be applied in this interpolation technique, I have to assume something that is going to be serve as a last equation. For example, the most common assumption that is more usually used in spline interpolation is that the second derivative of the first function at the first data point is going to be 0. So this is an assumption that is most commonly used. You can use other assumptions, but the most commonly used assumption is this, that the second derivative at the first data point is equal to 0. So if you find out the second derivative of this the first function, it is going to be 2a1, that is going to be equal to 0 at the first data point. So that means a1 equal to 0. So now I have 3n minus 1 equations here, and I have the last assumption, the last equation here. So that means in total I have 3n equations. So I have 3n number of unknown constants, and I have found 3n number of equations that can that's why I can easily solve all of these equation, the system of equation to find out the unknown constants. So if I look at an example, I think it would be more clear to you. Let's say I have these data points x equal to 3, 4.5, 7 and 9. So this is x0, x1, x2 and x3, and I have corresponding function values f of x0, f of x2, x1, f of x2 and f of x3. So I need to use the quadratic spline interpolation. Since there are 4 data points, so I have 4 data points, that means number of equations equal to should have to be something like that. There are n plus 1 data points. I have n plus 1 equal to 4. That means n equal to 3. So I would have to find 3n number of equations. Since there are 4 data points, there are 3 intervals. That means at each interval I would have to determine 3 coefficients. So in total there are 9 equations that I have to solve for 9 unknown coefficients. Okay, so that's the main purpose of these examples. So I have to determine these 9 equations. So under the first category, I would have 2n minus 2 number of equations. Since the value of n equal to 3, I would have 4 equations under this category. Similarly, under the second category, I would have 2 equations, and in the third category, I would have n minus 1 equations. That means 3 minus 1 equal to 2 equations. And finally, I would have a final equation, that means the assumption that the second derivative at the first data point is equal to 0. So these are the equations that I would have to determine. Okay, so let's start from the first type of equations. Type 1 equations, they look something like this. So how did we get those? We just apply these equations under the first category. If you just remember from a couple of slides before, that these two equations actually denote the conditions that are applied at the interior nodes. In our example, the interior nodes are x equal to 4.5 and x equal to 7. So at x equal to 4.5, if we apply these two equations, I would get these two equations, type 1 equations. Similarly, at the other interior node x equal to 7, if I apply this x equal to 7 into these two equations, I would get other two equations. So I have just found the 4 equations that I had to under the category 1. Similarly, category 2 equations denotes that the function values at the two end data points, at the boundary data points, are equal. That means the functions must pass through the boundary points. So the boundary conditions, the boundary equations should look something like this. So if you just apply the boundary points, that means x equal to 3 at the first interpolating polynomial, so I would get this equation, and at the last boundary point I would apply the last boundary point x equal to 9 at this equation, and I would get this one. So these are the two boundary equations that I am going to find out under this category. Similarly, for the third category, I need to have two equations that I have already said. These two equations denote that the derivative of the functions at the interior nodes are going to be equal. So this equation, this condition was under the category 3. So if I apply these condition at two of the interior nodes, the first interior node was x equal to 4.5 and the second interior node is x equal to 7. So using these two interior nodes, I would get two equations. Okay, so there are in total 1 2 3 4 5 6 7 8 equations, but I need to have 9 equations, so I need to have another equation. So if you remember, the final assumption was that a1 equal to 0. So I have found just 9 equations that I had to. So if I just rearrange all of these equations into a matrix form, I would get something like this. This is the coefficient matrix, this one is the coefficient matrix, and this one is the unknown vectors that I would have to determine, and this one is the constant matrix. So I can easily use the I can easily use the Gaussian eliminations or Gauss-Jordan methods or Gauss-Seidel methods that I have covered in lesson 17 to lesson 25. So please go through those lessons to solve these such kind of equations. So Gaussian elimination, Gauss-Jordan or Gauss-Seidel or Thomas algorithm, whatever it is. So you can easily apply those techniques, solving techniques, to solve such a system of linear equations. So once you solve this system, you would get the unknown coefficients, something like this. These are the unknown coefficients that I had to determine to find out the 3 interval data points, the 3 interval function, that means quadratic interpolation functions. So in the first interval from 3 to 4.5, if I apply a1, b1 and c1, I would get an equation something like this. In the second interval from 4.5 to 7, if I apply a2, b2 and c2, I would get a function that applies in these interval. Similarly, in the third interval, I can easily get the function. So each of these functions are applicable at each of these 3 intervals. So I have to be careful that I apply the specific function at specific interval. Okay, so this function is going to be applicable only within this interval. So f2 is going to be applicable only within this interval from 4.5 to 7. So I have to be careful about that. Okay, so this was the table. In the table we were given 4 data points. Within the first interval 3 and 4.5, I get this function. Within the second interval 4.5 and 7, I can get the f2x interval, f2x interpolating polynomial. Similarly, in the third interval from 7 to 9, I get this final quadratic interpolation polynomial. Okay, so that's the result. So now let's say I want to find out the value x equal to 5. So x equal to 5 is within the second interval. So that's why I need to use the second spline interpolating function. So if I just substitute x equal to 5 into the second interpolating polynomial, I would get a function something like this. So something like this, and the result is 0.66. That means that is the result as x equal to 5. Okay, so I would just use the second interval because x equal to 5 is situated in the second interval. So I can easily extend the idea of quadratic interpolation to cubic spline interpolation. In that case, I would have to use a third order interpolating polynomial at each of the intervals. So the third order interpolating polynomial something looks like this. The order of the polynomial is 3, and that's why I would have 4 unknown constants at each of the intervals. So in the quadratic interpolation case, I would have to determine 3n number of equations, but in the case of cubic spline, I would have to determine 4n number of equations. So the number of equations is greater than here, greater than the quadratic interpolation, because I have more constants here. Okay. Similarly, if you want to use cubic fourth order spline interpolation or fifth order spline interpolation, that would cost you a more number of equations and a more number of computer memory. So that is not preferable here. So in spline interpolation, the main purpose of spline interpolation is that I use the lower order interpolation polynomial to get the most appropriate features of the data points. So I do not need to go for higher order interpolation polynomials. So up to cubic spline interpolation, that is the main limit that we actually use in practical purposes. So we do not need to find out the fourth order or fifth order spline interpolation, because in those cases actually the main limitation comes here, because spline interpolation was actually used for lower order interpolation polynomials within each interval. Okay, so that's the main purpose here for using spline interpolation. For cubic spline interpolation, let's say how we are going to find out the equations. I would have to find 4n number of equations. So since there are n plus 1 data points, so there will be n minus 1 intervals. So at each interval I would have 4 unknown constants. So I would have 4n minus 4 conditions. Okay, so the functions must be equal at each of the interior nodes. This is the first category of equation. Similarly, the first and the last equation must pass through the endpoints. That means there are 2 conditions there. The first derivative of the interior nodes must be used. There are n minus 1 conditions here. Similarly, the second derivatives at the interior nodes must be equal. There are n minus 1 conditions here. So if you remember, in the quadratic interpolation we did not have to calculate the second derivatives, because if you differentiate a second order interpolation formula, it would cost you, it would result in something like a constant. So that means nothing. So that's why we did not use the second derivative in the case of quadratic interpolation. But in spline interpolation, cubic spline interpolation, we can use the second derivative. So that will result into another n-1 condition. So similarly, the second derivatives at the end of the NORs are 0, so that results in 2 conditions. So in total there are 4 n equations. So I am not going to show you the case of cubic spline interpolation. That's a homework for you. So how you can determine those 4 n conditions, please go through the details of the quadratic interpolation so that you can easily determine the equations that are going to be used for cubic spline interpolation. So that's the end of the spline interpolation. In this lesson we have learned about linear splines, quadratic splines and cubic splines. We have seen how the constants or unknown constants can be easily determined using the conditions, specific conditions at each of the internal and boundary data points. We have also seen an example using quadratic interpolation, so you can easily extend that example for cubic spline or higher order splines, but higher order splines are not preferable here. Okay, so please try out the MATLAB code that I have attached here in this video for linear, quadratic and cubic splines. So go through the details of the code. So that's the end of this lesson. So in the next lesson we are going to show you the multi-dimensional interpolation. So that is very much interesting, because in this lesson in this lesson and the previous lessons I have shown you how interpolation was used for one-dimensional data. That means I had one independent variable x. But what about other, if you have other independent variables, that means 2 independent variables or 3 independent variables? That's what makes you the multi-dimensional interpolation, and that's very interesting. I hope you will like those videos. So please go through the details of this spline interpolation before going to the multi-dimensional interpolation. So till then, thank you so much.